All right, so I think I have everybody. Here's who I don't have yet. Let me know if I missed you. Sarah B, Matt, Emma, Stuart, Darwin, Jules, Doa, Matthew, Colin, Sarah T, McKenna. But I got everybody else. Okay, so it sounds like we're good. Oh, here's one. Sarah B. Okay, time to get started then. Okay, so last time we were talking about this, this what I like to call this. Oh, I forgot to put my mask on. This strategic diagram. And again, this is a quick reminder. There's no rigor in this diagram. This isn't a theorem. Everything that I feel like is kind of encoded in this diagram is stuff that we've already stated and talked about in more detail elsewhere previously. So what this is just kind of a way to organize the ideas. So we already talked about it. I don't want to go through all the details again, but the point is, if you compose things in this order, like this, then you have this lifetime of 2 that allows you to keep track of, a bunch of different ideas, some geometric, some algebraic, but with one concept, the lifetime of 2. Right? We also talked about how while these theorems, independent of each other, look like, well, they're completely different things. On the one hand, this theorem here is computing an accumulation of change. This theorem is computing an accumulation of circulation. They're totally different geometric concepts. True, absolutely, they are. But they are both special cases of this larger theorem that we don't really have the tools to talk about. And while we can't talk about the larger theorem, we can see the shadows of it, the sort of the effects of it being there. By the pattern that shows up in this diagram. So, and again, I don't want to review everything we already said, but if you take a gradient of some function, if you take the boundary of a curve, then evaluating the original function on those boundary points like so, versus evaluating the vector field over the gradient vector field over the original curve as a line integral like so, you get the same thing, right? And the point is not that there is a sort of a, what I like to call a diagram chase that describes a theorem. The point is it's the exact same pattern over here. Green's operator, boundary, line integral of the vector field along the boundary curve is the same as the double integral of Green's operator over the original region. Equal. Exact same pattern on this diagram. So again, it's really no coincidence that this pattern holds, because again, really it's all the same theorem, and this diagram is just kind of a like I like to call it a shadow of the real actual mathematical object that we use to describe and prove the big all-encompassing theorem. The way we're going to use it in this class is as a memory tool and as a sort of a pattern recognition kind of thing. And by the way, for whatever it might be worth, I think this is nice. But if you're having kind of some trouble understanding, what's the deal with Green's operator? One way to think about it is to think, all right, well, Green's operator, it plays a role in this part of the story that is just analogous to the role that gradient plays in this part of the story. And so you can take what it is that you understand about gradient and, there obviously there's geometric differences and you got to adapt accordingly, but that will help you, that'll give you ideas for ways to maybe help you understand Green's operator and vice versa, etc. Okay, so, all right, we talked about all that last time. So last thing we're going to do in chapter 6 before we move on finally to chapter 7 is I am finally going to show you this method for finding anti-gradients. I want to note that what I'm going to show you is different than the one in the book. They're both fine. I think mine's easier. Everybody's got their different preferences though. So, if you like the book's way better, no problem. But yeah, I think mine is easier to execute. I think mine is easier to understand. And I think mine is easier to follow when you're looking at someone's work. So keeping in mind that, your goal when you're writing out, solutions to homework problems or solutions to exam questions, your goal is not to get the answer. Your goal is to explain a line of reasoning and to effectively communicate that reasoning. Having a method that is easier to follow is helpful to that goal of making your work easier to follow, therefore better communicated. Okay, all right, enough of that. Yeah, suppose you've got a vector field, and let's suppose for a moment that it actually is a gradient. So let's suppose that it is a gradient. Well, of course, this is what a gradient is, a gradient of some function that, this mystery f that we haven't found yet. A gradient is made up of partial derivatives. So if that's the case, well, that means, among other things, the first component of the vector field is the x partial of this function that we're trying to find. Which, by the way, that means, I'm going to say now, I'm going to restate this statement here, just slightly, just sort of grammatically backwards, if you will. That means that this function f that I'm trying to find is the x antipartial of that first component p. Then likewise for the other components, q is the y partial, and therefore the function that I'm trying to find is the y antipartial of q. And then, likewise for z, r being the z partial means the function I'm looking for is the z antipartial of r. Okay, so punchline is, what our method boils down to is take these components. Let's see, keep overshooting. Let me slow it down. There we go. P, Q, and R. Take their antipartials with respect to x, y, and z respectively, right? And the function you're looking for has to equal to all three of those. All right. Now, where it gets a little confusing, a little complicated, whenever you talk about antiderivatives, of course, there's integration constants. When you're talking about partial derivatives, the integration constant is what we call a partial constant, right? The whole reason that we have something over here, this thing that I'm calling C1, is that, well, really, f really has to be is something that when I take the x partial, f has to be something that when I take the x partial, I got to get p. So that arranges for the x partial to be p. But if I were to add in anything whose x partial is 0, it doesn't change anything, right? So when I say that f has to equal to your x antipartial of p, all I mean is not necessarily the antipartial that you happen to write down, right? It could be any of the antipartials. And to consider all possibilities, you do have to therefore add in this what we call a partial constant, otherwise known as a function. It's just that it's a function with no x's in it. Okay. All right, so what is this function, and likewise, what are these functions? Well, we don't know, and that's why this becomes kind of a sort of a game process of trying to figure out what those functions might possibly be. And I'm just going to show you an example to see how that plays out. Here's the vector field that I want to find the antigradient for, and notice I take the first component there, second component there, third component there. I'm taking the x, y, and z partials respectively. Again, the order matters. You got to do the right ones with the right ones. And in so doing, here's my antipartials. Well, I mean, these are the antipartials that I just happened to write down. Are these three things all equal to each other? No, they're all different. That's okay. Because all I really need is for these to all be equal. I need for there to be a function that is equal to all of these. I am allowed to add in a function of y and z to that. Right? Yes.
So we just always leave it like that.
No, we're not done yet. No, yeah. No, there's a whole, we're not done yet. Well, there's a whole process to come. Yeah. So this is sort of the beginning of the game, as it were. So this could be any function of y and z, and I just need for there to be an f that's equal. Yeah, the f has to equal to this, but C1 can be any function of y and z. And likewise, f has to equal to this, but C2 can be any function of x and z, etc. So the slick move is to, now again, here's where we sort of start a game. And I think to myself, well, I see an x squared y there. I see an x squared y there. I don't see an x squared y in here. But you know what I could do? I could make this x squared y, and that's fine. So that, I mean, so we've kind of matched up some terms here. All three of these do indeed have this same term. It's just that one of them is the mystery partial constant function. Then likewise, I see that, I see this, and you know what? This could be xz, because again, the only rule is it's just not allowed to have any y's in it. So cool. And then lastly, I have minus yz squared, minus yz squared. And yeah, you know what? This is perfectly allowed to be minus yz squared. So altogether then, the function that I'm looking for that's equal to all three of these things, and again, it's got nothing to do with whether the ones you happen to write down first all happen to be the right one. No, that's not how it works. There is a function equal to all three of these things, and it's this that has, you see, the green term and the blue term and the orange term. So again, kind of a game, kind of a, you know, can I make these partial constant functions be, you know, within what they're allowed to be? Can I let them be what they need to be to make all three of these things equal to the same thing? And in this case, yes. Everybody see the process? Does that resolve your question? Yeah. Okay. Yeah. Okay. All right. Again, this doesn't always work because there are vector fields for which there are no antigradients, right? We already saw last time that just, you know, whenever Green's operator is not zero, then there is no antigradient, right? So what'll happen there is you'll end up with a game. You'll end up with a mix and match sort of, you know, can I make this work, that you just can't make work. It's just not possible. And when you sort of realize you're playing a game that, yeah, there's no way this isn't working, then there's your key. Okay, so moving along. Done with chapter 6. Off into chapter 7. So real brief, big picture of what chapter 7's about is it's about basically the same stuff as chapter 6. Pretty much. It's just that in chapter 6, we were looking at the 2-dimensional version. And here in chapter 7, we're going to be looking at the 3-dimensional version. So we're going to be looking at different kinds of integrals, oriented integrals that we can look at in 3 dimensions. And we're going to have to define some new ones. Well, a new one in particular. Well, kind of some. Anyway, depends how you look at it. Then we're going to start looking for accumulation theorems. Right. So in the same sense that Green's theorem, you know, where did we get Green's theorem from? Well, we found a mathematical object that had the feature of accumulation, and we gave it a name, and we observed that it has all the right properties, and we wrote down the result that, yeah, it accumulates. It's just like mass. It's just algebraic. And then we eventually did the same thing for the fundamental theorem of line integrals. So we're going to be doing the same thing here in 3 dimensions, and we're going to find 3 accumulation theorems in 3 dimensions, kind of like how we found 2. In fact, let me go back to this diagram here. Whoops. Yeah. Yeah, kind of like we found 2 accumulation theorems in 2 dimensions. We're going to find 3 accumulation theorems in 3 dimensions. Okay. All right. So, but we got to build up some tools first. We're going to start off with talking about parameterized surfaces. This is machinery that we need in order to be able to write down and talk about the objects that we're going to be playing with. We need to be able to parameterize surfaces. Now, y'all have seen a parameterized surface previously. Y'all have previously seen back in chapter 1, long ago, right? Y'all have seen a parameterization of a plane. So here's that again. Let me just remind you how this works. The idea is that this x naught represents a point in the plane. This V1 represents some vector parallel to the plane. And if that's parallel to the plane, then if I take a multiple of it, then I will again have something parallel to the plane. And then likewise, V2, something parallel to the plane, but in a different direction, means that any multiple of it also parallel to the plane. And the big idea then is that if I start in the plane, right, x naught is in the plane, and then if I move parallel to the plane, you start in the plane, you move parallel to the plane, then guess what, where you end up? Still in the plane, right? And so that gives you also still points in the plane. And I think it's geometrically satisfying that you can sort of play with S and T. S and T can be any numbers, whatever. I mean, that just gives you different vectors parallel to the plane. It's all good. As you play with S and T, you can kind of trace out the whole plane. Yeah. Okay, so I hope that rings some bells. Back from chapter 1. Okay, is everybody happy? Okay, now, so one thing about, real quick, I'll comment. One thing about, you know what, I can do this now. One thing about a parametric surface is that there's, again, 2 parameters. It's not just the one parameter, right? So we have the 2 parameters, both S and T. Another way to think of it is that our domain for the parameterization is R2, because there's 2 inputs, S and T. So there was a visualization perspective that we had on parametric lines, parametric curves, that, hey, just let the parameter be time. Well, we now have 2 parameters, and we don't have, outside of science fiction stuff, we don't have the ability to think about 2 different kinds of time, right? I think that'd be a great movie. I would totally watch it, but it's not really something that we can make good sense out of. Does that make sense to everybody? So that's the one thing you got to let go of. Parametric surfaces are just like parametric curves, except you can't think of them as being traced out over time. You just have to think of them as it's a surface generated by a function coming from 2 parameters instead of 1 parameter. Okay. All righty. Now I'm going to show you how to make a bunch of parameterizations. The book spends a bunch of time talking about parameterizations. The thing that's a little disappointing for me is that the vast majority of the book's time on parameterizations starts with the parameterization. They say, hey, here's a function that parameterizes something, and starting with that function, that parameterization given, they then go to interpreting, well, what does it look like? That's kind of the opposite of what y'all really need, to be totally honest. What y'all will need in practice is, hey, I got this surface here. I need to do chapter 7 kind of stuff with this surface, which is going to require me to have a parameterization of this surface. How do I create the parameterization? Right? So the books, again, focuses on turning parameterizations into surfaces. We're going to need to turn surfaces into parameterizations. So all of my examples here are of that latter category. I do encourage you to take a look at what the book has. The book's examples are nice examples, and it is useful to be, to help you get a sense for what a parameterization is. To, look at a parameterization. Book goes through and explains what that surface resulting looks like, right? That's good stuff. But arguably really more, we need this. Okay. All right. So the first tool that I'm going to give you is what I like to call the graph parameterization. It's a wonderfully simple trick. And that says that if you are looking at a graph, flashbacks to chapter 1, is it chapter 1 or chapter, I forget where, maybe that's in chapter 2. But early in the course, when we talked about graphs and equations and level sets and all that business, right? Specifically, if you have a graph, then the move, what I call the graph parameterization, is to take your two parameters, excuse me, your two input variables, and let them be your parameters. That's the move right there. And then you'd be amazed. Everything just falls into place. It's this one move. Whatever your input variables are, those are your parameters. Okay, let me show you how this plays out and how everything just magically falls into place. So here we're looking at a graph. Z is a function of X and Y. And following the advice above, I'm going to let my input variables be my parameters. So X is S and Y is T. And then what? Everything, I don't really have any choice on what I'm going to call Z, because I already know that X and Y are S and T, and that means that Z has to be S squared plus T squared. And lo and behold, as required, we have position XYZ as a function of two parameters, S and T. It just works. Here's another example. This is what you might call a sideways example, but here, instead of having Z be a function of X and Y, here instead we're going to look at Y being a function of X and Z. And the same trick, totally. Same trick, absolutely works. So here, of course, my two input parameters, my two input variables are X and Z. And so X and Z being my inputs, I'm going to let those be my parameters. X is S, Z is T. And what's Y? What's going to be my formula for Y? Do I get any choice in what Y might be? Nope. My hands are tied. I've got, and it says right here, Y is that function of X and Z, and X and Z, it has already been set. X and Z are S and T, and that means that Y just has to be that thing. Is that cool? Question?
Yeah, we were just thinking that maybe the algebra is different. This might be like that, but like I think you should.
Did I do it wrong?
Y and then,
It
should be like the y, I think it'll be like you and then I do.
Oh, I forgot a couple of minus signs, didn't I? Yeah, I'm sorry, because I divided by this. So there should be some minus signs in the exponents. Thank you for catching that. This is, again, what happens when you teach a course for the first time. So when I divided, those exponents should have gone negative. Yeah, thank you for noticing. I'll get that fixed. Okay, now why did I solve for Y? Oh, I shouldn't erase that. I should leave that there. But why did I solve for Y in this equation? We started off looking at this equation. How come I solved for Y? Why didn't I just solve for Z like a normal person, right? Isn't Z supposed to be the one that you solve? No, whatever. Solve for whichever one you feel like, or in this case, whichever one you possibly can. Because I'll point out, if you try to solve for Z here, you're out of luck. You can't solve for Z. It's algebraically impossible. So you can't solve for Z, and likewise, you can't solve for X. So in this case, I solved for Y because I didn't have any other choices. Y was the only thing I could solve for. And so, well, having no other options, that's the one I picked. Does that make sense? All right. Okay. You can also do this in other coordinate systems. It actually works out pretty much the same. Here, I have what you might call a spherical graph, because I have one of these spherical coordinates solved for and written as a function of the other two. And so cosine phi is a function of phi and theta. Now, yes, I know there's no thetas in there. That's okay. The way that this function depends on theta is super boring, right? But nevertheless, this is a function of phi and theta. It's just a really boring function of theta. So with that being the case, I'm just gonna leave phi and theta as phi and theta. I mean, by the way, why did I rename x as s and z as t? Why didn't I just leave them as x and z? And it's because then I would have x and z would be both input variables and output variables for the same function, and you're not really supposed to do that. I mean, it's super gauche, right? So no such problem here. X, Y, and Z it's fine to have X, Y, and Z be functions of just phi and theta. They are, in fact, different variables. I guess I could call them S and T, but there's no actual point in doing that. So when I say let the input variables be the parameters, cool, they are my parameters, phi and theta. I don't even need to rename them. And then just plug in for what you know about rho, just like we did in the previous cases. Rho, cosine theta. Cool. There it is. I plugged in rho is cosine phi. Rho is cosine phi. There you go. So again, it's really literally a graph parameterization. It's just a spherical graph parameterization. And again, we get position as a function of two parameters, phi and theta. Okay. Everybody good? This is my favorite parameterization trick, is the graph parameterization. I don't want to quantify, but yeah, I'm still going to say kind of most of the time, graph parameterizations are the easiest way to parameterize something. So that's why I bring you this trick first. Okay, here's another trick. Using vectors. You may recall that back in chapter 1, I guess it was, when we were parameterizing curves, we did, I think we did an example with a bicycle wheel. Y'all remember the bicycle wheel and the reflector? And as the bicycle rides down the road, then the reflector does this weird thing. And how do you parameterize that curve? And the idea was to understand the reflector as being, well, a sum of a bunch of independently more easily understood vectors, and understand the vectors independently and then bring them together. So this example is a surface example motivated by the same idea, and a little bit of a weird example, but weird is good. So I'm going to start off with this surface and pretend that's like the top of my head or whatever. And then, you grab the charged, anode, cathode, however that works, right? And make your hair stand on end, right? And so let's suppose that at every point on my head, there is a hair of length 1 sticking up exactly perpendicular to my head, right? And the tips, the hair ends, are what make up my surface S. And so this is what I want to parameterize. Everybody see the question? I understand what the premise is. It's weird, but it's not the weirdest thing ever. Okay, so how do we parameterize this? So the first thing I'm going to do is I'm going to parameterize the original surface. And so again, my original surface, this thing here, the original surface is a graph. See? Original surface is a graph. I can use the graph parameterization. That part's easy. So I have a vector describing position on the surface S. Yeah, right. Okay. Side note, this surface S, I can also view it as being a level set of that function there. Now, the reason I have to mention this is just kind of segueing into the next bit, but the reason I need to observe that it is a level set is because I need to figure out how to move in the correct direction. I need to be able to move in the in direction here. And so I need any vector perpendicular to the surface, and conveniently, the gradient of the function whose level set you're looking at is perpendicular to the surface whose level set you're looking at, right? Yes. G is it's the name that I'm giving to this function whose level set is my original surface. Yeah. So in other words, I took all of this stuff and I moved it over to the other side of the equation to, yeah, right. Cool. Okay. All right, so I've got this green vector now. But the thing is, that's not what I want to add. Oh, by the way, I have this green vector, but it's written in terms of X's and Y's. I need everything written in terms of S and T, right? So just don't forget S and T are X and Y. And so there you go. Everybody happy? Yep.
So what is the level set then? Like, I know what a level set is, but what?
Yeah.
What's the representation?
So it's the level set business is a way for me to describe this surface, and you can describe a surface in different ways for different purposes, right? So it's more convenient to start off with for me to view this surface as being a graph, so that I can do the graph parameterization, and that was very convenient at that moment. But having done that, and now deciding that I'd like to find this vector perpendicular to the surface, well, then it's more convenient for me to understand the surface as being a level set. And because if I'm viewing a surface as a level set, then the gradient's perpendicular to the surface.
So where in that level set does it indicate that the hairs are like one?
Well, I haven't gotten there yet.
So
Yeah, no, no.
Could be like hairs.
Right now, all I'm trying to do is find a vector that is perpendicular to the surface, right? And I found one. This vector here is perpendicular to the surface. But then the next step is what you're describing. Now I've got to figure out how to find a unit vector in that direction. So you're just getting ahead of me.
So the level set is not the surface.
Yeah, the level set's this surface. Yeah.
So the surface and it's the vector.
So this surface S is that level set.
Oh, S, not H. Okay.
Yeah. Cool. Okay. All right. So yeah, so we've got points on the surface are parameterized like that. Now I've got this green vector that I can describe like that. Does this help get me to the point on H that I want? Well, not really. What I really need is this unit vector that I'm going to call in. That's pointing in the same direction as the gradient, but it needs to be a unit vector. How do we get a unit vector? No problem. Divide by the magnitude. And that gives me that blue vector, which is still not quite what I want, because what I really need is this point. Right, that dark blue right there, that point that I'm interested in, that's on my surface H, right? That's part of this surface I'm actually trying to parameterize. Is, well, it's the point on the original surface S plus this blue vector here, there, and purple plus light blue is what gets me to a point on that surface H that I'm actually interested in. So what's interesting about this method, so again, it's a lot like the bicycle example, really. It's, I mean, it's, it's a surface instead of a curve, but the point is it was not hard to write down that purple vector. And it wasn't that bad. It was a totally different little bit, but, figuring out that light blue unit normal vector was, that's a completely independent thing, right? But once you have the purple points and the light blue vector, then the surface we're actually interested in is just a little vector addition. Yep.
So the problem saying the hairs were like one.
I'm having trouble hearing you. I'm sorry.
The problem saying that the hairs were like one was just so that we know that it has to be a unit vector.
Yeah. That's right. Hairs of length 1 is why I had to do this bit here. Yep.
So it was like another like this something.
Then I'd have to find a vector of whatever was, if you wanted to be length 3, then you'd find the unit vector and then multiply that by 3. Yeah. Yep. Okay, so the point of this example is not the particulars of the example itself. The point to this example is sometimes the thing that you're interested in is more easily understood as a sum of easier things. And when that's the case, break it down and look at each individual part separately and then use vector algebra. Yeah.
Geometrically, even though S is a paraboloid,
Uh-huh.
do not consider H a paraboloid.
It is not a, well, oh gosh, I have to admit, I'm not 100% clear if it even is a paraboloid. I don't think it, no, in fact, it's not a paraboloid. Yeah, it's just something weird. I don't know what it is. Yeah. Okay, good deal. All right, here's another example. Coordinates. Now, again, this is not a theorem. This is just an example. The motivation for this example is because it's a good sort of like, example of an idea that you can emulate to have a tool in your toolbox, right? So it's, try to think in terms of how you would apply this in other situations. The actual specifics of the torus are, marginally interesting, I suppose. So yeah, so we want to parameterize a torus, and a torus basically a surface of a donut, right? Okay. So the idea here is to try to start with this idea of thinking in terms of coordinates on the surface. And what I mean by coordinates in this case are, if you were going to try to describe location to someone and be like, okay, yeah, here's the numbers that describe where I am on the surface of this torus. How would you do it? For example, on the surface of the Earth, there's a pretty well established way to describe where you are on the surface of the Earth, longitude and latitude, right? It's two numbers. You communicate to me those two numbers and I can say, okay, well, I know how longitude and latitude are defined, and then I can play the game and I can, there I am. Does that make sense? So we just kind of have to do that same sort of thing now on the surface of a torus. And I think there's kind of a longitude and latitude kind of like point of view that you could take, right? So it goes like this. I'm going to use, let's see, let me zoom so I can see better. I'm going to think of starting at like that point on the kind of the outside, the outside part of where the torus hits the x-axis. And first, let's let T be that angle that says how much do you go sort of up from the, what you might call the equator, right? And so that's kind of like latitude, sort of, kind of, right? It's how much up from the equator. It's a little bit like latitude. And then what you might call kind of a longitude-like thing is then, okay, well, and then how far do you have to sort of, slide over side? How far do you have to rotate over? What is that angle there? Which is kind of like longitude. So don't worry yet about what that means about how we create a parameterization. My first goal is to make sure that we understand what I mean by these are coordinates that help me understand where I am on this surface. Is that cool? Everybody happy with that part? Okay. Okay, so now what do we actually do with this? First thing I'm going to do, I'm not going to go straight for the point that's described by S and T. It's going to take a minute. What I want to do first is let's talk about this point here. And that's what I'm going to call P. That's this point right there. So how do I describe P? And let me zoom because, again, it's a lot going on here. Okay, so that point P, in order to describe where that is, notice it's a sum of two vectors, right? And so this is a trick that we talked about earlier, but it's that vector there plus that vector there. It's green plus orange. Everybody see that? Okay. All right. So, okay, we write that down. The green vector is easy. There's that green vector. It's just A0, 0. And then let's see the orange. Oh, it won't quite fit on the screen there. Okay, the orange vector here. Now this one's a little trickier. That orange vector. And keep in mind, we're talking about the vector, not the points there, right? That vector, it's just a little bit of trig, but as t increases, that just kind of goes around in a little circle. And I claim that it's this. Notice that orange vector, the y-coordinate is always 0. Right, that orange vector, as I have it drawn there, is always in the xz plane. So y is always 0, and x and z are doing like that. How are we doing on that? Is everybody okay so far? Okay. All right, not the point we want. Right. This is this again, that point P. It's this point here. What I'm interested in is this point here, but we've made some progress, and in particular, I can get to the point that I want by just now rotating. I said, tell you what, I'm going to erase I'm going to retrieve some of these colors. If I just rotate by this angle, if I rotate by that angle S, that'll turn my dark blue point into the purple point I'm trying to find. Okay, so how do we do that rotation? And here's where we invoke some linear algebra. The rotation counterclockwise, you'll notice, around the z-axis, right? It's a linear algebra thing. Rotations are linear transformations. Linear transformations are represented by matrices. The matrix is what you get by applying the linear transformation to the standard basis vectors. And E1 rotates sort of to that, which is this, and E2 rotates to that, which is like that. And of course, E3 being on the z-axis, when you rotate around the z-axis, doesn't move. So now I went really quickly through that because, again, that's Math 218, that's linear algebra, but good thing to make sure you think through. Rotations are linear transformations. Linear transformations are represented by matrices. Matrices are understood as their columns, and the columns are the images of the standard basis vectors. Okay, so again, make sure you can do all the details of that process. Okay, so we're really close to being done with this parameterization now. We know this dark blue point P there's P. I know further that the dark blue point, if I rotate per that angle S, as I just made a matrix for, that gets me to the point that I actually want. So purple is the green rotation of the blue point. Let's write that down. Purple, what I'm actually interested in, is the green rotation of that blue point. And we've already found that blue point. There it is. Here's our green rotation, and matrix multiply, and it gives you this. So there's your parameterization of the surface of the donut, or parameterization of a torus. Yes?
When you said that, like, you set up the rotation matrix to go counterclockwise, does
Yeah.
it actually, like, matter? Like, if you
Oh, it's arbitrary. So roughly speaking, where that comes from is that when I set up these coordinates, right, I set up S to be this angle measured in the counterclockwise direction. Now, if you want to, for whatever reason, if you felt like there was a good reason to, buck convention, so I'm going to define, west longitude, right? Go Western hemisphere, right? I want, Western longitude, then yeah, you could, right? But, the problem then is that your S, my S is theta. And so I get to use convenient sort of like, memory of formulas from cylindrical coordinates and stuff like that. Yeah. So it's just a choice, but I think this is a good choice. I mean, I would strongly advise against choosing the other. Yeah. Good question. Anybody else? Okay. So takeaways on this example. Yeah, there's a bunch of geometry in here. Yeah, okay. The geometry is going to be different in every example. The big takeaway, the reason I showed you this example is because the foot in the door, the thing that allowed the process to start, was when I defined these coordinates. When I decided I'm going to describe location on the surface of this donut with, I see kind of a longitude latitude thing going on here. And once you make that choice, you've got those down, then it's just, there's certain geometric games that happen to work out to make things, to give us what we want. In this case, it'll be who knows what in other cases. So yeah, sure. While we're at it, let's remember that being good with linear algebra is also, very helpful, and adding vectors and a bunch of little particulars that followed. But the big point is set up coordinates sometimes is your first foot in the door. Okay. All righty. Last couple of examples I'm going to do here. These are actually really quick, but deforming a parameterization that you already have, right? So suppose, for example, I want to parameterize this ellipsoid. How would I parameterize an ellipsoid? I'm going to start by parameterizing something different that I know how to deform. So in particular, I have an existing parameterization of the unit sphere right there, right? This is, you might say that this is the spherical graph parameterization, where the formula for rho is just 1. Okay, so I have this existing parameterization. By the way, I'm going to rewrite this parameterization as a set of 3 equations. You'll see why in just a moment. And let's see, that's not what I wanted though. I want the ellipsoid. What's the relationship between this sphere and this ellipsoid? Well, we all remember this ellipsoid from chapter, I want to say 2, but anyway, from long ago, right? And we know that what's happened here is X has been stretched out by a factor of A. Right? And likewise, Y has been stretched out by a factor of B, etc. So one way you can think about how to parameterize our ellipsoid is to say, okay, well, X got stretched out by a factor of A. Okay, here, I'll stretch out so you can see it right here. My my X coordinate here is literally A times as big as it was up there. And similarly, the Y gets stretched by a factor of B. Okay, here you go. Now my Y coordinate is B times as big as it used to be. Now, alternatively, you can also just literally do the same substitution. So here I replaced X with X over A. You could do exactly that same thing in the equation. You could say, all right, I'm going to replace X with x over a. And the thing is, it gets you to the same result, right? Look at this. This equation here is exactly the same as, here, let me keep in mind, this is giving me position, x, y, z. That green equation is exactly the same as that green equation. So same answer. I mean, written a little differently, but same answer. So take your preference, whichever way you like better will get you there. But that's how you do that. So moral, if you have a parameterization that is easily deformed into what you're trying to parameterize, start with your existing parameterization and just think about how the deformation works. Okay, we're out of time, so this is a good stopping point. I've already made this observation. The book's done a bunch of examples. They're kind of backwards, but nevertheless, give those a look. Y'all have a great weekend and see you on Monday. Oh, yeah.